Hello, and welcome to my video on error intervals. In order to calculate an error interval, you will be given information on how a measurement has been rounded or truncated. This will be to a given number of decimal places, significant figures or unit. I will show you how to calculate an upper and lower bound for the measurement in order to write down its error interval. The video will work through a set of worked examples to cover all types of rounding and truncation. First of all, let's start with some definitions to help us calculate an upper and lower bound, and hence an error interval for a measurement or value when it has been rounded. When a measurement is rounded to a given unit, the actual measurement can be up to half a unit bigger or smaller. The lower bound for an actual measurement is the rounded measurement minus half a unit, and the upper bound is the rounded measurement plus half a unit. The measurement is greater than or equal to the lower bound and less than the upper bound. If the measurement were equal to the upper bound, it would round up to the next unit. The error interval is simply the measurement or value placed between the lower and upper bounds expressed as an inequality. Now for some worked examples. We'll start with some questions that give you the degree of accuracy as a given unit. Then we'll move on to questions with values that are rounded to a number of decimal places or significant figures. In these cases, you will first calculate the degree of accuracy as a unit. This will enable you to calculate the upper and lower bound. In question 1, the distance, let's call this d, has been measured to the nearest 1 meter. Hence, the degree of accuracy is 1 meter. We need to halve this and take it away from 15 to find the lower bound, 14.5 meters, and add it to 15 to find the upper bound, 15.5 meters. The error interval is then, d is greater than or equal to 14.5 meters, and less than 15.5 meters expressed as an inequality. Note that we can choose to use the distance d, or write the given distance in the inequality, both answers are correct. In question 2, the width of the rectangle, x, has been measured to the nearest 5 mm, so the degree of accuracy is 5 mm. Half of 5 is 2.5. We take 2.5 away from 55 to find the lower bound, 52.5 mm, and add it to 55 to find the upper bound, 57.5 mm. The error interval is then, x is greater than or equal to 52.5 mm and less than 57.5 mm expressed as an inequality. The next two questions are rounded to a number of decimal places. In question 3, the width of the bookcase is correct to 1 decimal place, so it has been measured to the nearest 0.1 centimeters. Hence, the degree of accuracy is 0.1 centimeters. Half of 0.1 is 0.05. The lower bound is 183.6 minus 0.05, 183.55 centimeters, and the upper bound is 183.6 plus 0.05, 183.65 centimeters. The error interval is then the width is greater than or equal to 183.55 centimeters, and less than 183.65 centimeters written as an inequality. In question 4, the height of the cuboid is correct to 2 decimal places, so has been measured to the nearest 0.01 meters. Hence, the degree of accuracy is 0.01 meters. Half of 0.01 is 0.005. We take 0.005 away from 0.94 to find the lower bound, 0.935 meters, and add it to 0.94 to find the upper bound, 0.945 meters. The error interval is the inequality, height is greater than or equal to 0.935 meters and less than 0.945 meters. The next 3 questions are rounded to a number of significant figures. Let's look at question 5. If 300 is rounded to 1 significant figure, then it is rounded to the nearest 100, and this is the degree of accuracy. Half of 100 is 50. We take 50 away from 300 to give us the lower bound, 250, and add 50 to 300 to give us the upper bound, 350. The error interval is the inequality, x is greater than or equal to 250, and less than 350. Moving on to question 6. If 400 is rounded to 2 significant figures, then it is rounded to the nearest 10, and this is the degree of accuracy. Half of 10 is 5. We take 5 away from 400 to give us the lower bound, 395, and add 5 to 400 to give us the upper bound, 405. The error interval is the inequality, y is greater than or equal to 395, and less than 405. Finally, for rounded values, let's look at question 7. If z is rounded to 3 significant figures, then it is rounded to the nearest 100. The degree of accuracy is 100, and half of this is 50. We take 50 away from 14,100 to give us the lower bound, 14,050, and add 50 to 14,100 to give us the upper bound, 14,150. The error interval is the inequality, z is greater than or equal to 14,050, and less than 14,150. The examples considered so far have been for rounded measurements and values. You also need to know how to write an error interval for truncated values. You truncate decimal numbers by removing decimal places. For example, 15.6789 truncated to one decimal place would be 15.6. To truncate a number to, say, 3 significant figures, include the first 3 numbers and then fill in all the digits after the first 3 significant figures with zeros to make the number around the same size as the original value. For example, 52,665 truncated to 3 significant figures is 52,600. To enable us to calculate an error interval for truncated numbers, it is useful to remember some definitions. First, when a measurement is truncated to a given unit, the actual measurement can be up to a whole unit bigger, but not smaller than the measurement. For example, if we had a brick of mass 1.799999 kilograms, if its mass was truncated to one decimal place it would be 1.7 kilogram. This means that the lower bound is the truncated measurement, and the upper bound is the truncated measurement, plus the unit of accuracy. The measurement is greater than or equal to the lower bound and less than the upper bound. If the measurement were equal to the upper bound, it would truncate to the next unit. The error interval is simply the measurement placed between the lower and upper bounds expressed as an inequality. Let's do a few worked examples. In question 8, the mass of a cake, m, has been truncated to 2 decimal places, so the unit of accuracy is 0.01 kilogram. The lower bound is equal to the truncated measurement, 2.35 kilogram. The upper bound is the truncated measurement, 2.35 kilograms plus the unit of accuracy, 0.01 kilograms, which gives 2.36 kilogram. The error interval is the inequality, m is greater than or equal to 2.35 kilograms and less than 2.36 kilogram. In question 9, the length of some fabric, L, has been truncated to 2 significant figures, so the unit of accuracy is 10 meters. The lower bound is equal to the truncated length, 210 meters. The upper bound is the truncated length, 210 meters plus the unit of accuracy, 10 meters, which gives 220 meters. The error interval is the inequality, L is greater than or equal to 210 meters and less than 220 meters. Thank you for watching my video. I hope you can now calculate upper and lower bounds and use them to construct error intervals. If you have found the content useful, then please consider subscribing to my channel.